It's really great work what we've seen so far this evening. Sorry I couldn't join yesterday. You guys are really doing the kinds of things that need to be done and that we just talk about. So it's really encouraging to see the projects on the ground. Dan and I published this book a couple of years ago. As he reminded, it actually came out exactly 5 years ago, but it's a 2019 print, but on Foundations for Sustainability, where we did kind of a deep dive into some of the more philosophical, theoretical underpinnings of why we think that we are failing at sustainability. And so we're going to touch on some of those topics in this talk. So it'll be quite a bit different from the really cool on the ground and art stuff we've heard so far, but hopefully is interesting. I'm also impressed there's still 34 people on the call on a Friday night at almost 7 o'clock. I'll cover the first part, but Dan, did you want to say something, introduce yourself right now?
I could just say I worked with Brian on this and on other collaborations. I'm an ecologist and sustainability researcher out in Western Maryland.
Excellent. Yeah, I didn't introduce myself either, I guess. I'm a professor in the Department of Biological Sciences at Towson University, which is just north of Baltimore, also in Maryland, and also a part-time researcher at a research institute in Austria. So we have that. In fact, that's the picture of the research institute. Dan was out there last year at this time for a conference that we had. So the title of the talk is Foundations for Sustainability. The idea that everything is connected to everything, but we think we also have some ways of showing that and building a quantitative science around that. So jumping right in, why are we here? Well, because we know that we are in overshoot space right now. The ecological footprint is greater than the biocapacity of the planet, and it has been now for several decades and only getting worse as we build up an ecological debt. And so we clearly need to be doing things differently. One of our main kind of take-home messages is that too much of the attention is treating on the outside of those rings, things like the symptoms and the problems that we see, which are real problems, but they don't actually address the core, the bullseye of that target. And that bullseye is really a function of flawed relationships that we have with ourselves and with nature. And we need to realign that before we can have any hope of making systemic changes to all the symptoms that we'll see. And Dan will get into that more in his part of the presentation. I like to remind people that most of the problems, if not all the problems that we have today, were actually solutions to yesterday's problems. So we're really good at having unintended consequences because we don't use systems thinking and long-term thinking. And we hopefully can start to do better and avoid just kicking the can down the road and making messes tomorrow with better approaches. One other piece of framing on this that I think is important to get across is how we view the environment is also, I think, flawed. It's too fragmented and too separated. And we tend to think of the environment as something separate from us and something out there. I use, a picture like this to show that, we're here and we're not nature. Nature is out there somewhere. When, of course, we know that we are drinking nature and eating nature and breathing nature and interacting with nature intimately, continuously. And so we need to reframe that in all things that we do and think. And so we have this alternative model, which looks at the system not as separate from its environment, but actually as the focus of two different environments. So everything that is out there is really just a temporary holding point for a flow that is going from somewhere to somewhere else. And we can start to take this input environment, output environment, and ask questions like, where does it come from? Where is it going? And how is it all connected together? And this is actually the basis for a network science, because when you start to build flows and processes together like that, you're essentially building out different networks. And so this is this kind of theory that we have, this network-based environment theory, which is formalizing this way of thinking, which is holistic, but also, as I said, like it's a formal grounded theory. This is really the origins of networks, is how things are each interacting through their input and output environments with other things. So what I want to do, which is probably a mistake on a Friday evening, but to take you through some mathematics. And just from I'm showing you numbers, but it's really to get the concepts across. It's not to run with the models. But But I think this to get this point across of how we can really quantify how everything is connected to everything else. And so this is a food web model that we have here. It's a well-studied food web model published now over 40 years ago, where people went out in the field. It was an oyster reef off the coast of South Carolina, I believe, and they were measuring how much standing stock, how much oysters were there, how much of the predators were there, and so on. So there are these different biological compartments that are part of that ecosystem. They were able to quantify, how much was there, and they were also able to quantify how much is flowing from one part to another in that model. And so they came back. It's fairly simple, actually, 6 compartments. A lot of the models nowadays are much more complex than that, but it's a good start, and it can show some of the things that we want to get across. The first thing is that any network is as a picture is actually a graph, which is a mathematical structure. And as a graph, you can convert that to a matrix, which is a matrix of connections, essentially. So it's ones and zeros. If there's a connection, there's a 1. If there's not a connection, there's a 0. So in this particular system, we had 12 arrows between the compartments. So we have 12 ones in our 6x6 matrix representing those connections. And where the math comes in next is that if you take powers of that adjacency matrix, of that direct connection matrix, it will actually tell you now, the numbers are changing in this matrix, as you see. It's telling you the number of pathways that exist between any 2 compartments that take 2 steps to get there, because it's the A squared matrix. So we now have a way of looking at indirect pathways, that take 2 steps to get there. Well, you can carry on and say the A cubed matrix is actually 3-step pathways, A to the 4th or 4-step pathways, and 5-step pathways, and so on. So the math actually works to be able to identify at least the exact number of pathways that you will get as you're taking more and more steps, right, to get around from one thing to another. You should notice a couple of things immediately, is that the numbers are getting large quickly, right? So with only 5 steps, we're up to more than a dozen in many of those. And so so these are complex networks. Even with only 6 compartments, you now have many different ways of things transferring, connecting, communicating, and so on. And just to carry that a little bit further, if you were to take A to the 10th, which would be the 10-step pathways, you're now in the hundreds of different connections. And A to the 20th, you're now into the millions in some cases. So only 20 steps in 6 compartments, you have a million distinct different pathways. These are all distinct, individual, unique pathways to get from any one compartment to the other one, right? So, very complex, but a lot going on, right? And so this is what this network approach is able to dig out for us. And one of the things that comes out of that is that ability to identify not only the direct, but the indirect flows and indirect relations, is that we find that there is a preponderance of a lot of mutualistic relations that emerge. So even though it's built on direct connections of one organism or one functional group eating another functional group, the net sum of all those indirect interactions actually tends to be overwhelmingly mutualistic. And that's really not penetrated into the ecology textbooks yet. We're working on that, but it's really a new vision for ecology, not beyond just the red and tooth and claw predator-prey relations, but also recognizing all of these mutualistic relations, which is essentially a bounty of the commons. It's a spillover benefit from being in a network. So when you're in a network, when you're a player in a network, you benefit from the actions of the other players in that network. Sure, you have direct exchanges with those immediately around you, but you are also getting a lot of benefit. And as an example for that, back to this simple 6-compartment oyster reef model. So this matrix now on the right is showing you the direct relations. And actually the way that you read this is you look at the pairwise connections across this main diagonal. So this would be a plus minus, meaning it's a predation relation. There's one is gaining and one is losing. In this case, it's a 0 and a 0. That means they're just not having a direct connection. But in the direct matrix, they're all going to be either 0, 0 or plus minus, because it has to be 0 sum. But when you look at the whole system relations, it includes all those indirect influences. It's mostly positive signs. Of the 36 elements, 25 of them are now positive. So almost all of those neutralisms became mutualisms in an indirect setting. One of them became predation, right? I mean, it's not a guarantee that there'll be mutualism, but again, the tendency is that they become more mutualistic. So it's the importance of taking this holistic approach. When we try to reduce something and only look at part of it, we're we're going to clip away at those mutualisms that that we don't even know are there because we haven't been doing this assessment enough. And let me just make a short other quick dive into how that actually how those mutualisms arise. Was that if you were to have a food chain, like in n-dimensional food chain, you can actually do the same kind of math here, and you basically find out that in the food chain it's an either or. The one that's taking from you is taking from you, but the next one up is helping you because they're taking from the one taking from you, but the next one up from there is hurting you, and it's this cascading effect of plus minus signs the whole way. I mean, it still does turn out that the overall net sum of those benefits would be, you get 3 times the amount of positive benefit in a chain system, but it's not, but there's still quite a few predation indirect relations that are going on there. But we've also been able to show that if you turn that chain into a cycle, so now this is, I don't know if it's well represented, but it's going out and then coming back around. So this is an n-dimensional cycle that is existing there. And now when you do the indirect flows, you actually find out that you're only having a negative relation with the one immediately in front of you, the one that's taking from you, but every other one in the network you have a positive relationship with, which makes sense because you lose the flow to that one in front of you, but then to get it back again in the cycle, you rely on every other part of that cycle to get it back. So it actually turns out that the overall mutualism in this structure, as the number of compartments goes to infinity, is infinity. So it has maximum amount of benefit is a circular system. And that's also, I think, a pretty cool result of this, because we all know that we're trying to change from linear type of models to circular models, whether it's circular economy or what. Nature works in cycles, right? So this loss of circularity that we have done by soil erosion and biodiversity loss and everything else that's going on out there has actually been chipping away at all those mutualisms. And like I said, we don't even know we've lost them because we didn't know they were there in the first place. And so we're hoping to bring attention to the fact that these mutualisms exist, and also try to figure out how ways to put it back together so that we can benefit from the presence of this network mutualism. So so those were the couple pieces I wanted to get across. We'll have a discussion at the end. Kind of my take-home messages are about, its wholeness and not fragmentation. Dan will talk more about that life is not a machine. And I like this blue marble photograph because it shows the Earth all on one frame, and it shows the limits to the Earth, but also the fact that we should celebrate those limits because nature is doing pretty well managing within them. So with that, I'll turn it over to you, Dan. Just tell me when you want to change the slides.
Brian set a great foundation, a great starting point for where the assessment of framing the crisis and the solution that we're looking at, polycrisis, multi-crisis, meta-crisis. I heard a new one the other day. I forgot all the names for this that we're in. So I mentioned that I'm an ecologist and sustainability scientist. I have done work in soils, organic farming in 1992, graduate studies in soil nematode communities, and also in using carbon, nitrogen, and organic matter in sort of vertical layers in soils as an indicator of sustainability. So that's kind of where I learned ecology in the soil, is where I learned how to understand sustainability. It's where I learned how to try to develop indicators of sustainability and health. But right now I'm talking on a slightly different angle, which is kind of a planetary scale, sort of a general systems approach. And a lot of that was guided by Bob Ulanowitz, who was my PhD co-advisor, who has worked in that way. So I'll talk a little bit about framing this crisis some more. We've already talked about it some. And then some demonstrations to illustrate some principles that might be worth considering to get us out of it. And then another part is, what should we do? And so if part one is kind of like a paradigm or a conceptual model or worldview, metaphysics, so what? What does that mean we do today or tomorrow in the real world? Okay, so if you could go to the next one, I guess, Brian. I don't think I can do that, right? Because you've got that. So we've already seen this. Brian showed it and made the slide. I call it the global ecological multi-crisis. Each of these surface symptoms, if you want to call them that, I see them as linked. They're all interdependent. It's truly existential. The thing that keeps me talking about this is that it seems to be getting worse faster than people have modeled or predicted. So if you go on to the next one. So our approach, as ecologists, as systems ecologists, was a little different than some others. Some other folks might pick one of these, which is hard enough and a valid, battle. But we asked, what is it that all of these crises share? Like, what's in the center of this whole mess that we're in? And we came up in the book, our hypothesis that it's actually the paradigm of science, going back to Descartes and Newton and contemporaries, reductionists, mechanistic. There's a big focus on objectivity. There is an analytical approach. That's what we see to drive the technology that drives industrial culture that generates all of these symptoms. We have some evidence. We don't see this in indigenous cultures. And the world is literally turned into a machine that we've imagined it to be. It's acting like one. It's running out of gas. It's breaking down. This is the opposite of what ecosystems in the biosphere do. They improve themselves. That's why we have soils that grow spontaneously in depth and fertility. That's why we have an oxygen atmosphere. That's why we have an ozone layer. So we proposed an alternative that would kind of flip this around. If it's the system of ideas, it's the paradigm. There should be one that could generate solutions. We pulled it from many places, some very old citations. It ends up being very similar to indigenous knowledge. Donella Meadows was a thought leader on this, to use the paradigm because it's got the maximum leverage for change in a complex system. Okay, if you could go to the next one. So, we have these kind of foundational principles that we're proposing that in this alternative paradigm in the book, life is the basis of value. That's sort of going at science, which strives to be objective. But if you really kind of critically think about that, that's kind of a weak starting point. If you say that you're value neutral, you can be used for harmful things. So we propose it's much more important to assert the value of science is life. We also say the one Brian talked about, life environment is whole, it's not split. So you kind of have to change a biology textbook on page 1, where it's like, okay, biology is over here, environment's over here. And then the one I'll talk about today is that life and machine are categorically different. This was an amazing contribution that I learned about from Robert Rosen, but also Bob Ulanowitz. So these two guys that I've, cite the most, that we both cite the most, are Robert Rosen came from relational biology. He used category theory type of math. And his original question was to answer the question, what is life? But he came up with this interesting spin, which is to say, a better question is, why is life different than a machine? And the more I dig into this, the more I see how profound this is. He also pointed out that life is anticipatory. It uses the future to determine present behavior. Machines don't do that. Robert Ulanowitz in network ecology, network analysis, also information theory, philosophy, and even science and religion dialogue. He showed these 8 properties in which autocatalytic loops, again, going back to Brian's mention of cycles, how there's basically infinite mutuality. They have these 8 properties that machines and mechanisms don't do. You can see the list there. We could talk about them if anybody wants to. Okay, so the next one is a little more on these two topics. So Bob studied a lot of very well articulated networks like that Chesapeake Bay. I think that's like mesohaline section of the Chesapeake Bay in a season like the summer, where he and collaborators quantified all of the flows on who eats whom, and also the stocks. So the standing stocks, the population amounts, they would quantify carbon and other elements like nitrogen and others, and get what Brian said, these matrices, you do the math, you get all of the indirect relations, and you get a whole different picture of nature. He kind of focuses a lot on the autocatalytic loop, where there's a picture there of a very simple one, but it's very powerful. It's enough for him to say that autocatalysis is not a mechanism. All that positive feed forward. Autocatalytic systems exhibit properties that transcend the much overused metaphor of nature's machine. Rosen did a similar thing from a different angle. He was trying to model an organism, and what he came up with was a material system as an organism if and only if it is closed to efficient causation. And he goes on to describe, if you ask why F, the answer comes from inside the organism itself. I think of this, and I'm not sure it's exactly right, but it's like the organism is self-causing or self-creating, self-maintaining, self-sustaining. The F part of his equation there, his map diagram, is the metabolism, and the other Greek symbol, I can't always remember those. Is it phi or something like that? Is the repair part. So that's where you get this closure, where metabolism and repair are synergistically linked. Okay, so to me, these give us the basis to think of system archetypes. In a way, you can, it's an attempt to be a synthesis that doesn't destroy complexity. We try to keep the complexity, but I think we can say that machines are inherently unsustainable. A machine allows extraction of short-term profit. It's like the purpose of a machine, the function, the benefit you get from using it, but it's at the expense of environmental quality. It's using some kind of energy, it's generating waste, it's tearing itself down, and it's, if you really do the accounting, it's probably not a net profit. Life is categorically different. Environment is internalized and improved. Self-sustaining life environment system as a whole can go on indefinitely. Okay, keep going there. So this is a similar thing again, trying to get these in a place for something like a new kind of STEM education or STEAM, or put the art in there as well for science, technology, engineering, math, and art. I pointed out that the win-win relationship, the mutualism that Brian showed the math for between life and environment includes soils. So this is why soils grow in depth and fertility in a place like a forest or a prairie and other places. Life builds functional gradients. Tatiana, when you were talking about entropy, so there's some of these folks from Italy and other places who say that there's a counterbalancing universal principle of syntropy, which has not been appreciated. Other people call it self-organization. I think we see a lot of evidence that entropy does not necessarily have to rule. It has to exist, but it doesn't have to rule. On the other side there, a linear flow through system, in our industrial culture, we pump out fossil fuels or raw minerals, run it through our society and dump it as waste. There's a split between the system and its environment. It's a win-lose relationship. You get a short-term gain, but the environment degrades over time. This definitely is entropic. It's destroying functional gradients all over the place, including soils. So if the one research project I was talking about, if you compare long-term agriculture to old forest, the vertical gradient of the soil has been destroyed through the agriculture. Okay, so here is a little bit of something different, which I really kind of wasn't sure I was going to do, but I got inspired yesterday watching the last presentation of Emily and is it Nan, who did a great thing with their her sculpture of Columbus made of clay and potatoes, and just an amazing thing. This is, I'm a novice on this, but I'm trying to play around with doing something physical. I was going to demonstrate it, but I thought I couldn't get the technology to work. So it also relates to what Alex said, first speaker today. We often ignore or overlook things that we don't see or can't see. So relations are things we can't see, and system boundaries are things that are kind of like theoretical, or it's the thing you talk about indoors in a classroom or something like that. So how do you make that more real? Well, if you try to demonstrate the fact that a chipmunk is connected to its environment, one way to do it is disconnect it from its environment. So if you try to close it off in a jar, the thing that was striking me is that if anybody's watching that, and if I actually did it, and I would never do it, you would feel instantly like, no, stop, don't do that. There's a knowledge of this connection that maybe we've forgotten or lost access to. There's no such worry about a machine. It doesn't have that intimate, required, continual connection to the environment. Nobody's going to feel upset if I seal off my old cell phone in there and leave it. It doesn't matter. If you go to the next slide, now here's another way to demonstrate something about life. If I put a full ecosystem in that little chamber, it would have to be bigger, and close a chipmunk off in that, like a terrarium with lots of plants and soils. There's no such feeling of concern, right? Because that critter, even though it's closed off from the whole world, it has life support system. It's like a miniature version of the biosphere or the forest. Plants and soils are integral to life. These principles, you know, if this stuff holds up and we need to critique it and keep testing it, are possibly universal. You know, this life environment relationship could apply to all life, all environments, all humans, no matter how intelligent. So that was supposed to be Albert Einstein in there. I don't know if you can see his hair. Doesn't matter if you're a genius, you still have to abide by these laws of nature. And it's also toward reframing our idea of independence. It's sort of paradoxical that life actually gets its independence through interdependence, is my take-home message from ecology. Okay, so what should we do? You know, I've been studying ecology for 30 years, or if you want to go back to 1970 when I was playing with frogs in West Virginia, it's longer than that. I want to share ideas and collaborate. I went up to Governor's Island and New York and hanging out with these Urban Soil Institute folks, Tatiana and Paul and more. And I'm ready for some action. I think we have the science we need to create the solutions, a holistic, you could even call it old knowledge of our life environment is in us. It can be activated, and we can learn by doing in direct experience. You guys are the experts at that, and I want to learn more. A little bit, if another slide here, go ahead. So why, though, integrate all the way down to this sort of metaphysical or theoretical paradigm basis? Well, I think there are reasons to do it. For one thing, if you want to solve one of these problems, do it truly. Don't solve one problem over here and create two other ones over here and think that you've actually made any progress. That's not going to help it with a systemic problem. Also, solve it once. Don't do a partial effort and kick the can down the road. You know, I've got grandkids now. I'm trying to, you know, take care of my own shit, as one of your days was themed. Okay. There's also the systemic change leverage that Donnell Meadows said. If you can change the paradigm, you can change the whole system. So those are hypothetical reasons to integrate both the daily action and the whole worldview and paradigm. If you go to the next one. So as an example of something like Gaia soil and green roofs, it's great. It works instantly. It's already connected to the paradigm. But if we point out those connections and keep them all connected, there's some benefits. Somebody may be inspired by Gaia soil and green roofs and want to do it that way, but they may also like to know the underlying foundational paradigm and do something similar for a different application or location. I think there might be one more slide. Yeah, so I'm not going to go through all these. These are the ways I want to do some action. I think science needs to convert itself to sustainable facilities first. We should be leading by example. And Oberlin College, the Adam Joseph Lewis building that David Orr built is a great example to me. I think we should learn and follow from the leadership of indigenous peoples. They have the proven track record of knowing how to self-sustain on Earth for thousands of years. And this one is a little maybe different. So indigenous people are the leaders of sustaining life on Earth, but the space exploration community are the leaders of dispersing life beyond Earth. And I can't talk about it today, but there are reasons why those could be complementary and help each other. I already mentioned some curriculum for STEM. I'm calling it here now, art, science, technology, engineering, math education. I'd like to engage youth and all potential leaders at this new paradigm level. I have this idea that I would explain it, show these demos with chipmunks and stuff. 5 minutes later, people will be like, oh yeah, that's obvious. And then the kids will like fix it even better for me. So I want to learn from them. And I want to work more with Urban Soils Institute, Paul and Gaia Soil, and join your movement wherever I can. I think that was it.